Hello everyone and welcome. I'm excited to have you here today. We're going to be discussing a quick reference guide for engineers, focusing on key topics like heat load, CFM, chilled water, pumps, and cooling towers. This is a broad overview designed to give you the essentials you need for your projects. Over the next few slides, we'll cover each of these areas to help you better understand their roles and how they connect. Let's get started. Let's take a look at how we calculate heat load. The fundamental formula is Q equals A times the heat load factor, which is measured in BTU per hour per square foot. Essentially, this helps us estimate how much cooling capacity we need based on the area. Now, considering the Saudi conditions, for residential spaces, the heat load factor ranges from 25 to 30 BTU per hour per square foot. But for offices, it's a bit higher, around 30 to 35 BTU per hour per square foot, mainly because of increased solar gain due to larger windows and higher occupancy. Let's go through an example to see how this works in practice. Suppose we have a 50,000 square foot office. Using a heat load factor of 30 BTU per hour per square foot, we multiply 50,000 by 30, and that gives us 1,500,000 BTU per hour. To put that into more familiar terms, that's equivalent to about 125 tons of refrigeration, or TR. This calculation is crucial because it helps us determine the right size of cooling systems to ensure comfort and efficiency. It's all about matching the cooling capacity to the actual heat gain of the space, especially considering our local climate conditions. Let's take a look at how we calculate CFM, or cubic feet per minute, which is a key measure in our HVAC systems. The basic formula here is simple. 1 ton of refrigeration equals 400 CFM. So, whenever you're trying to determine the airflow required for a specific cooling load, you just multiply the tonnage by 400. For example, if you have a 125 TR system, you multiply 125 by 400, which gives you 50,000 CFM. This straightforward calculation helps us quickly estimate the airflow needed for proper system performance. Now, a quick note specific to our region, Saudi Arabia. When dealing with high ambient temperatures or infiltration, especially in coastal areas like Dammam, we need to account for additional airflow. In these cases, it's recommended to increase the calculated CFM by about 10 to 15%. This adjustment ensures the system can handle the increased load and maintain efficiency and comfort. So, understanding this calculation and adjustment is crucial for designing effective and reliable HVAC systems tailored to our local conditions. Let's talk about the chilled water flow rate, which is a key aspect of cooling system design. The main formula we use is GPM, or gallons per minute, and it's calculated by dividing the BTU per hour by 500 times the temperature difference, delta. For example, if you have a cooling load of 1,500,000 BTU per hour and a delta of 10 degrees F, then the flow rate would be 300 GPM. Now, in Saudi Arabia and many other regions, the typical delta for comfort cooling usually falls between 8 and 10 degrees F. This range is important because it balances efficient cooling and humidity control. If delta is too high, humidity can become an issue, affecting comfort. So, understanding this formula helps us ensure our systems are properly sized and efficient, ultimately delivering the comfort we aim for while optimizing energy use. Let's talk about pipe sizing based on GPM, or gallons per minute. The key rule here is straightforward. If your system needs 35 GPM, then you should use a 2-inch pipe. This helps ensure proper flow without causing unnecessary pressure drops or flow issues. Now, for larger systems, the sizing scales up accordingly. For example, if you have a main flow of around 300 GPM, you'd typically go with a 6-inch pipe. Of course, these are approximate sizes, but they give you a solid starting point for designing efficient piping systems. The most important concept to remember is that pipe size must match the flow requirements. Using the correct size helps maintain system efficiency and longevity. This approach ties back to our overall goal of optimizing system performance while avoiding problems like pressure loss or pipe damage. So always consider your flow needs carefully and select the appropriate pipe size accordingly. It's a simple rule, but it plays a critical role in the success of your piping design. Let's talk about chiller sizing. The key formula here is quite straightforward. TR, or tons of refrigeration, equals the total heat load in BTU per hour divided by 12,000. This helps us determine the capacity needed for the chiller to handle the cooling requirements effectively. For example, if your total heat load is 1,500,000 BTU per hour, you simply divide that by 12,000, which gives you a chiller capacity of 125 TR. Now, it's important to keep in mind that in regions like Saudi Arabia, where ambient temperatures can reach up to 50 degrees C, we recommend adding a safety margin of about 10 to 15%. This extra buffer ensures the chiller can operate efficiently and reliably even under extreme conditions. So, in summary, use this formula to size your chillers accurately, but always factor in those safety margins for the hottest days. This approach ensures your cooling system remains robust and dependable all year round. Let's take a closer look at how we calculate the pump head and power. The key formula here is P in kilowatts, which equals the flow rate Q times the head H times 9.81, divided by the efficiency eta times 1,000. Now, what does this mean in practice? Well, Q represents the flow rate in cubic meters per second, H is the head or height in meters, and 9.81 is the acceleration due to gravity in meters per second squared. The efficiency, eta, accounts for how effectively the pump converts input power into hydraulic energy. To make this clearer, let's look at an example. Suppose our flow rate Q is 0.02 cubic meters per second, the head H is 30 meters, and the pump efficiency eta is 0.75. Plugging these into the formula, we get a power requirement of about 7.85 kilowatts. This calculation is essential because it helps us determine the right pump size and ensure energy efficiency in our system. Remember, understanding how these variables interact allows us to optimize performance and reduce operational costs. So, grasping this formula is a key step toward designing effective pumping systems that meet our project needs efficiently. Let's talk about the heat load estimation methods, specifically the BTU versus WM2 approach. The first one, the BTU per hour per square foot method, is commonly used in American and ASHRAE-based designs. It's great for quick load estimates, especially during early project phases. On the other hand, the W per square meter method is preferred in SI metric systems and is more precise, making it suitable for detailed design calculations. A key point to remember is the conversion factor between these units. 1 WM2 equals approximately 0.3169 BTU/HRFT2. For context, a typical heat load in Saudi conditions is about 30 BTU/HRFT2, which converts to around 95 WM2. In practice, I recommend using the BTU method for tender estimates because it's faster and more straightforward. But for the detailed design, especially when precision matters, the WM2 method is the way to go. And don't forget, in coastal areas like Dammam, where high ambient temperatures and humidity are common, it's wise to add an extra 10 to 15% to your estimates to account for the increased cooling load. Overall, understanding when and how to use each method ensures accurate sizing of HVAC systems and efficient project planning. Let's talk about condenser sizing specifically for Dammam, Saudi Arabia. The ambient temperatures here can reach peak levels of 46 to 50 degrees Celsius, which is quite high. Because of these extreme conditions, we need to derate or reduce the capacity of air-cooled condensers by about 10 to 15% from their nominal ratings to ensure reliable operation. In practical terms, this means if you have a condenser rated at 100 TR, the actual effective capacity under Dammam conditions would be around 88 TR, considering a 12% derate as an example. To maintain the desired 100 TR capacity, you'd need to size the condenser larger, specifically about 114 TR, so it compensates for the derating. Additionally, to optimize performance in such hot climates, it's recommended to use enhanced fin spacing, around 14 to 16 fins per inch, and high airflow fans. These adjustments help improve heat dissipation and keep the system running efficiently. Understanding these factors is crucial for proper condenser selection in Dammam's demanding environment, ensuring your system remains effective and reliable even in extreme heat.